for the kind words of introduction. And at the outset, let me thank the INSA selection committee and the INSA council for selecting me for this honor. It's a great privilege to be associated with one of the heroes of Indian science, Homi Bhabha. Given that the award is for like a work over an extended period, I thought I should talk about a theme which is like been a fascination of mine from the time of my PhD and continues to fascinate me. I've continued to work on it with students, postdocs, and so on. And this is about strongly correlated quantum impurities. And I should acknowledge funding support from Department of Science and Technology and CRB. Okay, yes, I have to find. Yeah, so what's the aim and plan of my talk is to provide a historical perspective on the evolution of this subject and the important role it has played from the 50s to the present. I hope I can, it's a little technical actually, but I hope I've tried very hard to make it accessible to a non-specialist audience. I hope all of you will get something out of it by the end of the lecture. So I start with an introduction to the quantum impurity problem. In quantum impurities that you are very familiar with, namely quantum impurity in semiconductors and non-magnetic quantum impurities, and then go on to talk about what's the difference between them and what I call correlated quantum impurities. I talk about some of the models and some of the problems that it led to, their solution, and then I talk about a very strange development that took place, which is that sometime about 20-30 years ago, high temperature superconductors were invented, and one of the standard models for treating that is like the Hubbard model. It's a lattice model. I'll tell you what it is. And then a development came called dynamical mean field theory, which actually maps this lattice problem back to one site picked out as if it's an impurity embedded in a background which is treated as a medium, and it's back to the quantum impurity problem that we had been working on. So it kind of revived this field, and I've worked quite a bit on that problem. I will tell you some examples. And you can also do, instead of picking out one site, you can pick out a cluster of sites of this lattice and treat that as an effective impurity. And that leads to a different kind of, it's called a cluster extension of DMFT. I'll tell you about it. And I'm going to comment on other extensions and challenges, and end my talk about a new kind of quantum impurity that likely to play a big role in the future, called NV minus center and diamond. So it's a lot to get through. I hope, I'll skip probably some of the technical parts, but I hope you'll get a flavor of what I'm talking about. All right. So just a little caveat that it's a field with a long, rich history, and this perspective will have many limitations. It's incomplete. It's bound to skip many important subtopics. It's subjective. It involves my personal bias, and I will not be able to assign credit for contributions. So the aim is to give you a flavor of some of the physics involved, and with snippets of a subset of the research contributions by me and collaborators in this area. And I apologize at the outset to some of the experts in the audience and to people whose contribution I'm bound to leave out. Okay. All right. With that said, so let me begin with quantum impurity that most of you would have heard about, which is N-type, for example, N-type donor or N-type impurities in semiconductors. These are the impurity, the word impurity has a connotation that it's something that we don't want, right? Normally that's like the common parlance word. But this impurity runs our lives in the form of all the semiconductor electronics that you use and carry around in your pockets. So here, basically, for example, if I take something like silicon and then replace one of the silicon atoms by an impurity atom with 5 electrons. Silicon has 4 outer shell electrons, and it's bonded tetrahedrally. This is like a 2D caricature of the tetrahedral structure. And if I have another impurity with 5 electrons, that impurity will substitute for the silicon, and then there is 1 electron left over. And the question is, what does it do? So this impurity actually has an effective charge which is +1. So this extra electron sees something that's like a hydrogen-like atom there. So it will form a hydrogenic orbital, which is actually very big. And so it will form a state below the conduction band. I'm pretty sure most of you know that semiconductors have a sort of valence band, and it's going back. Yeah, I'm sure you're familiar that most of the semiconductors have a valence band which is completely filled with electrons. It has many conduction levels. All of them are occupied by electrons, and there's a conduction band which is completely empty. But this extra electron doesn't go into the conduction band because it sees this hydrogenic attractive center. So it forms a bound state below the bottom of the conduction band, and it's like a hydrogenic wave function which is localized around that impurity, which decays exponentially fast. And and because the energy difference between that level and the conduction band is very small, at very small temperatures, many of these electrons are excited into the conduction band, and that gives the properties of all the semiconductors. These are called doped semiconductors, which leads to the electronic, etc. But if you put non-magnetic quantum impurities in metals, the thing is very different, because in a metal, there is no such separation of a valence band and a conduction band. In fact, you can picture when the bands overlap, actually. So there's no separation. So what happens is that there are a large number of conduction electrons, and the potential that the electron sees is no longer the strong Coulomb potential. It sees something called a screened Coulomb potential. And then this impurity state now becomes what is called a virtual bound state. Now, the simplest example I can think of, you can think of a particle moving in a one-dimensional model potential of the sort that I've sketched. If the potential was to continue to infinity along those dotted lines that I've sketched, actually there would be a bound state, which is again exponentially decaying out beyond that potential well, exactly like a bound state in the semiconductor. But in a metal, actually, that the potential doesn't continue to infinity but comes back down because of the screening, and therefore this bound state kind of leaks into the metal and sort of has plane wave like oscillations. So this is called a virtual bound state. You have to actually picture the extension of this in 3 dimensions, where there's like a spherical shell kind of thing with a potential well inside. And then when you do this work was actually carried out by Friedel, and so you have to imagine spherical waves which are impinging on this impurity, the waves which correspond to electron states in the metallic state, and then they get scattered by this impurity and re-emerge as spherical waves, but with a phase shift, and that is called this delta. And there is a different phase shift for different orbital angular momenta because of spherical symmetry. And then Friedel showed that actually that the resistivity that contributed by these impurities in a metal is proportional to the square of this phase shift. And you can talk about like a density of states. In the previous slide, I actually drew a picture of the density of states there. And there you can see that the density of states is like a delta function at that bound state. But here, you'll find that you'll get a broadened density of states of this impurity levels. Okay. And this is a ubiquitous explanation for resistivity of metals with non-magnetic impurities, where all of them have some temperature dependence coming from other scattering mechanisms. And if you go to low enough temperatures, they all flatten out and give you this impurity resistivity, which I mentioned before. Okay. people put magnetic impurities into metals as long ago as 1934 and noticed that lots of unusual consequences, which is that the resistivity of those materials doesn't do what I just showed you of flattening out and coming to a constant at 0 temperature, but has a minimum in the resistance and then starts going up as you go down in temperature. And this remained a puzzle for 30 years until Kondo came up with an explanation, which I'll tell you about. In fact, in a very influential book by Wilson in the Theory of Metals in 1954, he said that this cause of this minimum is entirely obscure and constitutes a striking departure from well understood things. Okay. So early theoretical efforts used something called the ST exchange model to understand this. The notation may be slightly unfamiliar to those of you who don't work in this area, but let me explain what this means. In quantum mechanics, we work with operators. All observables are operators, and this is called the Hamiltonian, which is like the energy, an operator that represents the energy of the system. And if I have conduction electrons, I'm sorry, the pointer is not working. So if I have conduction electrons, I have a band with the energy epsilon of k, and then this is written for many electron system. So that n represents an operator which is the number of electrons in a particular k and with spin sigma. And then this impurity now, it's because it's magnetic, it has a spin, and it interacts with the spin of the conduction electron in the neighborhood of that impurity. So that is like spin dot conduction electron spin density interaction. That's what is written there in terms of operators that create electrons or destroy electrons. Okay. And then if you take such Hamiltonian, between two such, if I have many such impurities, the conduction electrons mediate an effective interaction between these impurities, and that's called Rk-Kb interaction, and that has this characteristic form of 1 over r to the power of 3. Okay. So in 1957 to 61, Friedel and Blandin used a slightly modified version of their virtual bound state model, where they said that the effective potential that the electron sees is spin dependent, and based on that they could explain some of the trends in magnetic versus non-magnetic behavior and the trends in residual resistivities for different impurities in metals, but they could not explain this resistance minimum, and that had to wait for Kondo. But before I do that, Anderson made a seminal proposal in 1961, which is called the Anderson impurity problem, and it's an explicit and simple realization of a virtual bound state end of local moment formation, and it's perhaps the most extensively studied quantum impurity model. Okay. So again, let me skip the Hamiltonian. I will sort of say it in words what is contained in that thing. Okay. So maybe not. Okay. So basically, what Anderson assumed is there is this impurity which is sort of trapped in a localized orbital, but because it's a virtual bound state, there's an amplitude for it to tunnel from that localized orbital. So it can leave that localized orbital and move to the conduction band, or go back from the conduction band to this localized orbital. But when it sits on that localized orbital, because it's localized, there's a strong Coulomb repulsion energy. So it has to pay an energy cost U. So this Vk in this equation is the amplitude for it to tunnel from this localized impurity to the conduction band, and there's a conduction band represented by that conduction band energies. There's a localized level, and then the U. These are the parameters that govern this Hamiltonian. And when U is in the non-interacting limit, when you neglect U, you can solve this problem exactly, and we do this normally in terms of something called the Green's function, which is kind of the amplitude for an electron to be found at that impurity with a certain energy omega. It's actually the probability it's the probability amplitude for finding that. And then, so you can use that to calculate this thing called the phase shift that I mentioned, and then you can look at the density of states. So let me skip the details, and you can see it looks like what Friedel envisaged. And so there's like a broadened peak at where the impurity level should be. But so what happens if you turn on U? And you can do something called the Hartree-Fock approximation, where you sort of, if for example one of the spins is already there, then the other spin sees an effective repulsion potential, and its local energy gets increased. So it's a simple way of treating this Hamiltonian. And then you can, so you can, for example, look at the density of states. Here on the left-hand side, I have looked at the magnetic case, and the right-hand side I plotted the non-magnetic case. In the non-magnetic case, basically there's a conduction band, and on top of that, this impurity with the density of states, which is the broadened density of states. Upspins and downspins are equally populating all the levels, so this impurity is non-magnetic. But if U is large enough, you can get the situation on the left side where the upspin is occupied, the impurity upspin level is occupied, but its downspin level is empty because its energy got increased and it went above the Fermi level. So, and there's another equivalent thing which is downspin occupied or the upspin empty. And so this is called the impurity with a local moment. So, and within the same model, Anderson could explain how some cases you get magnetic moments and some cases you don't get magnetic moment. And this model is actually closely connected to the exchange model that I showed you earlier, in the limit when U is very large. And here I've tried to picture the many electron levels of this system. Imagine there's a ground state in which, for example, the impurity is occupied with one electron. That is that central thing. And then all the conduction electrons are in their ground state, which is below the Fermi level. That's the ground state of the entire system. You have to think of this whole system as one quantum system with many, many possible excitations. Okay, now what can you do after that? Starting from that thing, you can have two kinds of excitation. One is you can change the number of electrons on the impurity. That makes, for example, if you remove an electron, that gives you one state with the impurity with no electron, and then conduction electron in its ground state. And on the right-hand side, if you put two electrons in the impurity, that is n sub d equal to 2, and then you have conduction electron in the ground states. So these are three different states of the same system. Now you can create excitation in the conduction electron. You can take a particle below the Fermi level, occupied in the occupied levels, and push it to an unoccupied level in the conduction band. There's an infinite number of them, very large number of conduction electron levels. And what this hybridization, which the V that I talked about, which allows electrons to tunnel from the impurity to the conduction and back, what it is doing is making the system undergo transition between one of these subspace of levels and another of these subspace of levels, and they all get mixed up horribly. And it's an extraordinarily complicated problem. But nevertheless, if this epsilon d and epsilon d plus u are very large compared to that hopping amplitude, you can do second order perturbation theory and treat it as a small perturbation and ask so there's a virtual transition electron make to these excited levels and come back, and you can ask what is the effect of that. And it turns out that effect is exactly an interaction between the spin of the once occupied impurity level and the conduction electron spins, the Hamiltonian that I exhibited before, and that J coupling which was there in that Hamiltonian is given by this formula. Okay. So Anderson kind of made a nice connection between this entire set of things which is up to this field. And then in 1964, Kondo, a Japanese physicist, calculated the resistivity of this model to an order which is higher than what people had calculated before. And he found a very interesting thing. He found that, so I've written the impurity contribution to the resistance here. And the leading term is that what I call rho naught, which is the density of states on the conduction electrons, times J, that's a dimensional number, the square of that, that's the leading term. Then when he calculated the next term, he found that it has a logarithm that depends on the temperature divided by the bandwidth of this impurities. I mean, of the conduction electrons. And then, which means this gives a rising contribution. As the temperature decreases, this logarithm increases and gives an increasing contribution to this impurity resistivity. And you remember all the other contributions from phonons or whatever other stuff is scattering, the electrons had a decreasing contribution. So you add the two together and you get the resistance minimum. And that was his explanation. And in fact, so this was the explanation of a long unsolved problem. So that's why everything associated with this now has become associated with the name of condo. Okay. So actually, if you calculate any property of this impurity to these higher orders, you'll find this kind of divergence, because it's a problem. It's a nasty thing, because if you keep reducing the temperature, you can see that coefficient of that. This is supposed to be a series, a perturbation series, right? So those coefficients of higher and higher orders are supposed to be small. But if the temperature becomes small enough, this is no longer a convergent series. It's like, it doesn't make sense. So the question is, so this left people with what is called the condo problem. You know, what happens if you go to low enough temperatures? And you cannot solve that problem by doing this perturbation theory anymore. So here is, in fact, I've written a list of so many different properties of the impurity that you can calculate, and all of them have this divergence. So there's a temperature scale that you can calculate from that, which is this exponential dependence on the coupling constant. And if the coupling constant is very small, this temperature is extremely small. But if the coupling constant becomes reasonable, this is a sizable temperature, and at that temperature, everything falls apart. I cannot figure out what is going to happen to this problem at low temperatures. So this is the problem, and there were a lot of different attempts to solve this problem in the 60s without success, and it was finally solved by Ken Wilson using something called the renormalization group method. So the reason for this divergence is actually because when you do these calculations in perturbation theory, you keep getting these integrals. This is a very simple integral, and this is the integral goes from temperature to the bandwidth, and that's where this logarithms coming from. And it turns out this is actually very similar to divergences that you get in quantum field theory and critical phenomena and many other fields. And it was handled by Wilson invented this renormalization group technique to handle those divergences. So therefore, he was very well equipped to handle this problem. So one of the ways that people attempted to handle this divergence early is with something called the scaling procedure, which was in fact an inspiration for Wilson to invent this renormalization group. So the idea is that if you go back to this integral, this logarithm, it's saying every interval in energy between kT and d naught is contributing to this logarithm. And there are a lot of those intervals, and then that's why the thing diverges. So what people said is, let's reduce that bandwidth by integrating out or eliminating these high energy electrons, but keep track of their effects on the low energy physics, and then ask what happens to these coupling constants. So I now invent a new effective Hamiltonian where the bandwidth has been reduced. Then you can show that that coupling constant J, which was there in the model Hamiltonian, will change a little bit. I can write a differential equation for how it changes as I keep reducing the bandwidth, and it turns out to be given by this equation here. And you can solve that, and then you can calculate lots of properties and show that all the properties will be actually functions of the temperature divided by this condo temperature, which I mentioned earlier. And you can write a series in a much different series in powers of 1 over the logarithm of t over tk, etc. More and more complicated functions of this. But this is still doesn't solve the divergence problem, because you can see when temperature becomes equal to Tk, that denominator is going to 0, and then I still have an infinity in the problem. It doesn't solve, but at least made it clear that every property should scale as a function of the condo temperature. And here I show you some experimental data, which is like a triumphant verification of this. There are many, many materials here, different impurities, combination of different magnetic impurities in different host metals. And all of them you can collapse. If you were to scale each of the data by 1 over the appropriate condo temperature, you can collapse all of them into one universal curve, which is experimentally known, but you're still not able to calculate it theoretically and show that it should be that curve. And that's the problem that Wilson was able to solve. Okay, here is, for example, how the specific heat scales with T over Tk. Okay. So there, like, the condo temperature varies all over the place. Condo temperatures from 1000 Kelvin down to 0.01 Kelvin. And there's a whole host of materials with, okay. So Wilson recognized this idea was the key to many of these problems and invented this thing called the renormalization group method, for which he got the Nobel Prize. And then he, in fact, in the renormalization group method, as he developed for critical phenomena, there was a control parameter, because they were very clever and invented some fictive control parameter, which was the dimensionality. Because it turned out that in critical phenomena, if you are in 4 dimensions, then you can handle all these divergences in a way. So they said, let's expand around 4 dimensions and pretend we are in 4 minus epsilon dimensions, and that epsilon becomes a small parameter. Even though in the end you put epsilon equal to 1, they found that actually somehow they could calculate properties and so on. But in the condo problem, it turns out that there's no small parameter. You're stuck. You can do this renormalization group procedure, but some coupling constant starts becoming large and large. You cannot do perturbation theory anymore. So he invented a completely new technique called numerical renormalization group. And so it's a little, how am I doing on time? Another? Oh, okay, good. All right, so I'll just tell you a little bit of the flavor of this thing. So in that integral, you remember I showed you where the logarithms come, d epsilon over epsilon. Okay, so what Wilson did is, of course, any numerical calculation, you cannot work with a continuum of electronic levels, because this continuum comes if you have a thermodynamic limit, you have an infinite sample. But as long as you have any finite sample, you have discrete energy levels. But the problem is, without discrete energy levels, you cannot set up a numerical scheme, because you have to work on the computer. But what he did was a clever way of discretizing this conduction band. Imagine you've gone to the continuum limit, so you have a continuum of conduction electron states. But then he said, let me make a logarithmic discretization. Like, you start from, imagine the electrons bands, electron energies go from minus d to plus d. Then you discretize in powers of a parameter lambda, which is bigger than 1, in a logarithmic fashion, so that each interval there and in that diagram gives you the same contribution to d epsilon over epsilon integral. Okay, that's the way it's been designed. And with this discretization, you can go through a whole lot of transformations, which I'll skip, because I have many other things to say, and get to the end. Basically, you can go through a whole lot of transformations of rewriting the Hamiltonian in terms of the discrete levels that correspond to these chosen intervals, and come up with this kind of Hamiltonian. Okay, so here the impurity, remember what the impurity was. The last 2 terms are the impurity terms. If you put an electron in the impurity, that is what that C dagger D, CD represents, is the number operator for putting an electron on the impurity. If you put it there, it has an energy epsilon D. And then if you try to put 2 electrons on the impurity, it costs you energy U. That's what those last 2 terms compare. The first term is a different way of writing the conduction electron Hamiltonian in this discrete basis, because what has been done is to the way these new bases that has been invented is that F0 represents some linear combination of conduction electron states, which is the most localized near the impurity. And that's the one that actually the impurity interacts with closely. In fact, when an impurity electron tunnels from an impurity state to the conduction band, it actually tunnels into that state. It doesn't tunnel very far away. It tunnels in a local state. But that localized state is not an eigenstate of the conduction electron Hamiltonian, because the conduction electron wants to propagate. So that localized state of the conduction electrons tunnels, if you like, or hops to another localized state which is slightly more extended. And that extended localized state tunnels to another state which is even more extended, and so on. So that's the way you bring back the fact that the conduction electrons actually like to propagate through the sample. So that leads to this Hamiltonian. Okay. So it's called the Wilson chain Hamiltonian. So notice the very nice structure of it. So there's this impurity all by itself. Then it couples only to this first conduction electron, localized, the closest, most localized conduction electron state you can make around the impurity. And that couples to F0 couples to F1, F1 couples to F2, F2 couples to F3, and so on. So as you're going down the chain, you're coupling to states which are more and more spread out. Okay. And corresponding to that, because of the Heisenberg uncertainty principle, the more spread out it is, the less its kinetic energy. So that term, that hopping is therefore getting reduced, lambda to the minus n by 2. The tunneling amplitude from one the nth localized state to the n plus 1th localized state of the conduction electron is decreasing. Okay, so there's kind of a hierarchy, nice hierarchy here. So the largest energy in this problem is this epsilon d and u. So Wilson invented like an iterated way of solving this problem. Now, if you want to solving this, what does it mean, solving? Solving means actually diagonalizing this Hamiltonian. Okay, so what does the diagonalization mean? This is actually, if you look at in quantum problems, basically the Hamiltonian, if you write like such a discrete basis, it becomes like a matrix. So the question is, what is the size of this matrix? And the size of the matrix is this total number of states that are possible in your system. Now you have an impurity which has actually 4 states, because it can have 1 electron upspin, 1 electron downspin, or no electron, or 2 electrons, up and down electrons. So that's 4 states. The next shell of conduction electron, which is F0, that also has 4 states, because you can have 1 no F0, 1 F0 with upspin, an F0 with downspin, or 2 F0s, up and downspin. So for every electron down the chain that you introduce, you bring in a factor of 4. So if you have just the impurity in F0, you have 4. Impurity can be in any of its 4 states, and the conduction electron can be in any of its 4 states, but the combination can be in any of 16 states. And so you can see that the number of states is going to go exponentially fast as you go down this chain. And so very soon, you are out of luck. You can't solve the problem in any computer. Okay? So what Wilson did was, because he had this hierarchy, he said that let's solve this impurity Hamiltonian first. It's just 4 states, diagonalize a 4 by 4 problem. Bring in its coupling to F0, you get a 16 states, diagonalize that problem, right? Then bring in the next one, you get 16 into 4, 64 states, diagonalize that problem. And as you keep growing, the number of states is growing, the matrix size is growing. But the point is, there's a hierarchy of energy scales in the problem. He said, after a while, he says, let's throw out the high energy states and truncate the Hamiltonian into what I can manage. So suppose I can the computer that I have allows me to do 1000 by 1000 or 1024 by 1024 problem. I will restrict the number. I'll let the numbers grow till 1024, and then once the number goes beyond, I just throw out the high energy states, and then reduce everything to the remaining thing, bring in the next electron, and then redo this and keep on iterating this procedure. So that's called the iterative diagonalization, and he invented this trick, and it completely solves the problem. Okay. So I will, so in fact you can kind of rescale it so that, so as you go down the stain, the energy levels are getting closer and closer, and you can rescale it so that it begins to look similar. And that's what he did. So you get this recursive relationship between the Hamiltonian. So let me, this recursion relation I've written down here. And so if you basically, what it's saying is that if I have gone up to n steps of that chain, I take that Hamiltonian and rescale it by this factor of lambda to the half, add this next coupling, rediagonalize, throw out, rescale, and I keep doing this, and so on. And it turns out that this actually is good enough to calculate the properties at a temperature scale, which is related to how far down you have to go. And when you do that, you get some very interesting I'm sorry, it's not scrolling. Yeah. So here's a picture of how the many electron levels that I've talked about go as you change the n. So for small n, this is in a limit. For example, I've drawn this picture in the limit when this u is very small compared to the bandwidth. Okay, and but nevertheless, u is much smaller than this hybridization amplitude. Okay, so initially, when because u is so small, all states of the impurity are equally, are like probable. So this is what is called the free impurity regime. So if you are at very high temperatures, for example, or impurity, upspin state, downspin state, doubly occupied state, empty state, all equally likely to be, with sizable probabilities. Okay, but then as you go down in temperature, you'll find that the low energy level structure completely changes, and in that middle regime, the only states of the impurity that are around, if you examine it, will be states in which the impurity is only once occupied. It's an upspin or a downspin. So that is what is called the local moment regime. And if you keep going down further for very large n, you found that at the large n, there's no impurity state anymore. It's been completely screened out and mixed up with the conduction electrons, and you'll find that it's just some effective conduction electrons remaining. So Wilson basically showed that the physics of this condo problem, or in fact in this particular case the Anderson impurity problem, goes from these three regimes, and in the end it's actually always this local moment is actually screened out completely by the conduction electrons. And so I was actually very privileged to go to Cornell just around the time when Wilson solved the condo problem. He actually did this for this condo Hamiltonian. And then they actually asked me, so a group of them, three professors got together and asked me whether I want to do the same thing for the Anderson impurity problem. It was a rare privilege, and I worked on that. And then, so here is actually, this first picture is the picture of Wilson's results, where he calculates the susceptibility times the temperature, the spin susceptibility of the impurity as a function of temperature. He completely calculated this. And then I did the calculation for the Anderson impurity problem and showed that that you can actually, you see that at very high temperatures, the Anderson impurity problem has a susceptibility T times chi, which is like the effective moment, which is only 1/4. 1/8, which is corresponds to this all impurity states being probable. But then as the temperature comes down, you can see it's rising to close to 1/4, which is corresponds to the local moment regime, and thereafter it's decreasing, and at low temperatures you can see it kind of maps nicely onto this curve. So the Anderson impurity is indistinguishable from the Corner impurity at low enough scales, and kind of showed how, and that works only if U is large, and this bottom left picture showed you what happens if you change the values of u, etc. So basically, we could completely understand the physics of this Anderson impurity problem using this procedure. And in all the cases, the low temperature regime is what is called a local Fermi liquid. Okay, so this kind of was the solution of this problem. Of course, starting from that setup, because we have all the many electron levels of this Hamiltonian, one can in principle calculate all kinds of other properties, including dynamic properties, frequency dependent properties. But still, the computational effort involved in doing all of those was very prohibitive in those days when I was doing the PhD, and I came back after my postdoc, and I could not do any of this work because there was no computer facilities of the sort that is required for this work. And then, but other people took up that challenge of computing frequency dependent properties. And recently I collaborated with one colleague, Rock Zitko, who is an expert in doing calculations of this thing. And this shows, for example, an asymmetric Anderson impurity model. We were looking at some spectral function, which is like a frequency dependent property, which is like the probability, the density of states of this impurity as a function of frequency as for various temperature, etc. And we are able to, all of that can be done using this renormalization group procedure. Okay. And there, after this method, then of course, a whole lot of methods people were invented for looking at this impurity problem. But still, I would say the numerical renormalization group is like the most powerful method for doing this problem. Okay, there are all kinds of numerical methods, which I don't have time to go into. So let me get to the Hubbard model. Okay, so that's so far about the impurities. But the Hubbard model is kind of actually very closely related to the Anderson model. Imagine like you had impurities, each of which, like you have a lattice, each of which is like an Anderson impurity, where electron can sit with some energy, or if you put 2 electrons there, it costs you a Coulomb energy, U. And then electron can move from one lattice site to another with some quantum amplitude, and that is called Tij. It's a way of writing that Hamiltonian, which I've said it in words. So electrons can move on the lattice, and if 2 electrons sit on one side, it costs them energy U. This model was invented by John Hubbard in 1963. And at half filling, it's actually the simplest model that leads to something called the Mott transition, okay, which I'll tell you a little more about. And so if the hopping parameter is the dominant parameter, U is small, this actually describes at half filling a paramagnetic metal. But because, imagine if U is 0, this is a model with one site per one electronic state per site, and you diagonalize this and you get a band of conduction electron states, and you have only one electron per this conduction electron band can accommodate 2 n electrons, where n is the number of lattice sites in the problem. But I have only n electrons because the 2n comes because it can have upspin or downspin, right? But I have only n electrons, so the band will be half filled and therefore it will be metallic. Okay, but if you make U very large, it costs too much energy in this half-filled band. Has all kinds of configuration where some of the sites are doubly occupied, and that costs too much energy. So if U is the dominant energy in the problem, two electrons would not like to sit in the same place, and therefore you have one electron sitting on each side, and then they cannot move, because every time one electron tries to move, it has to pay this Coulomb energy cost. So you will find that any motion of electron has energy which is a gap which is U. So basically you get an insulator. So as you tune U, you will go from a metallic phase to an insulating phase, and it's actually an antiferromagnetic insulating state, because there's interaction between the spins that is induced. And here I've tried to sketch this thing. This again was invented by Anderson actually, which is like, imagine I have a configuration where U is very large and I have some configuration of spins like this. And you can see that if an electron hops, I go to a virtual state in which it costs extra energy, but that's an excited state. And then I get back to this ground set of levels where, but I can come back with spins flipped, as I've tried to indicate. So there's an effective, so you can go from one configuration of the singly occupied sites to another spin configuration of singly occupied state. And there's an effective interaction between them, which you can show is this Heisenberg interaction. What is it called? Si dot Sj, between the spins. Okay. Now, what's the connection with the Hubbard model? Why is it interesting? Now, in 1996, I'm sure you've all heard of this development. Bednorz and Müller invented this set of materials called cuprate. And so the material that they worked with is called lanthanum strontium copper oxide. Okay, that's a material where the copper is sitting in planes. Each copper is surrounded by 4 oxygens on in the plane, and by 2 apical oxygens, and the lanthanum is sitting in a different plane. So the planes, the copper oxide plane, and the lanthanum oxide plane, a copper oxide plane, and so on. So all the cuprates have this ubiquitous structure of a copper oxide plane in the thing. And this one is a 40 Kelvin superconductor, and this yttrium is a 90 Kelvin superconductor, and there are some other mercury materials which have 120, 130 Kelvin superconductivity. And all of them have complicated phase diagrams. So you can dope the base material, lanthanum copper oxide, with strontium. It's called hole doping because it removes electrons from the copper, or you can put electron doping, add electrons, and all of them show superconductivity to varying degrees and a very complicated phase diagram. And 20, 30 years have given us something that looks like this, a phase diagram as a function of doping, okay, with temperature. At half filling, which is x equal to 0, no doping, it's actually an antiferromagnetic insulator, and the antiferromagnetic transition comes down as you dope, and then you have this superconducting dome, and you have another phase which is called a pseudo gap phase, where there is not a gap, it's not an insulator, but the density of states kind of has a dip near the Fermi level. That's why it's called a pseudo gap. And above the superconductor, there's something called a strange metal, where the resistivity looks linear in temperature to very high temperatures. Nobody understands that. So we call it a strange metal. It's metallic, it has a resistivity, but it looks linear, and the mechanism is not due to phonons or anything, so we don't understand exactly why it's linear. And then rightmost, there's something that looks like conventional metals. 10 minutes, okay, thank you. So this system breaks 3 central paradigms of 20th century physics, which is, one is band theory fails at x equals 0, because if you work out La lanthanum copper oxide and figure out what is the number of, it has one band which is half filled, so if it weren't for interactions, it would have been metallic, but it's insulating, so you know that interactions are playing a big role, like in the Hubbard model. And then this superconductor is not the conventional variety of superconductivity that was understood because of Bardeen, Cooper, Schrieffer. Okay, it doesn't obey that paradigm. It's a different kind of paradigm, and that strange metal doesn't behave like conventional metals. So this is one of like an outstanding, challenging problem in condensed matter theory. And Anderson suggested that the Hubbard model is actually a good model for understanding this thing. In fact, you can show from the crystal structure, and which I will not go into, that the effective low energy model for this copper oxide plane will be the 2-dimensional Hubbard model. So that's why people go back now to the Hubbard model and want to solve that, because in order to understand high temperature superconductivity. Okay. All right. So let me, okay. So come to dynamical mean field theory, right? So this is where dynamical mean field theory came in. So if I take, for example, something many of you might have heard of, this is something taught in elementary courses on magnetism, which is called the Curie-Weiss mean field theory of magnets, which is if I take a Hamiltonian like spin dot spin, you take out one of the spins and think of its coupling to all the neighboring spins as an effective magnetic field. Okay, and if you go to the limit, if you pretend that the problem is in actually a very large number of dimensions, then you can show using central limit theorem of probability that this term in brackets is actually not fluctuating. It's even though it's like it's because it's a sum of large number of terms, because the number of terms goes as the dimensionality, so it becomes like a non-fluctuating mean quantity, and you can calculate that self-consistently, and it gives you a reasonably good understanding of mean field theory. So this dynamical mean field theory is an analogous system. So you pretend that your Hubbard model is not in 3 dimensions or 2 dimensions, but in an infinite number of dimensions. And then you can show that each electron sees, therefore hops to a large number of different sites, and you can show that the interaction effects on those sites become negligible. So if you were to take one site and watch what's going on, you'll find that that electron is leaking to the other sites, and then interaction effects are negligible there, so it sees like a conduction electron bath. All the other sites correspond to a conduction electron bath, and then from that bath it comes back to the site, and when it sights, it experiences this repulsion energy. So this is actually exactly the Anderson impurity problem, except that you have to make, this is any typical site of the system, so you have to make sure that the whole thing is self-consistent. So there's I will not go into the technical details, so there's a way of doing this, so that if you could solve the impurity problem, imagine you had like this thing called the self-energy, which is like how the local energy of the impurity site gets changed due to the interaction with due to U, and because it hybridizes with the conduction band. If I can calculate that by solving the impurity problem, and then I can put that, I pretend that that self-energy is the same as the self-energy of the lattice problem, which is actually correct, exactly correct in infinite dimensions, and then I put that back into the lattice Green's function, and I can actually recalculate that local propagator, and then using something called the Dyson equation, I come back to this impurity problem, and I sort of go through a cycle, like this iterative cycle again and again, and if I solve this problem, I would have got an approximate solution for the lattice problem. So the hard step here is actually solving this impurity problem for arbitrary hybridization, because hybridization now is not the simple form that was in the Anderson impurity problem, but could be energy dependent. So I have to solve this problem for arbitrary hybridization. Even the numerical renormalization group is kind of pretty much the best method for doing that. Yeah, okay. So, all right, so you can do that. So it turns out that this is actually a very good way of solving lattice problems, and we've done a whole bunch of them. Here, for example, there's a metal insulated transition in V2O3, which is, you can see that the resistivity jumps by orders of magnitude across some transitions, and by using something called the compressible Hubbard model, we could explain this stuff. So some work that I've done, I think, since I'm running out of time. So we also did some similar, invented a model for something called colossal magnetoresistance in manganites, where the magnetoresistance, which is the fractional change in resistivity, is 1,000 times larger than seen in normal metals. So, and that is a similar structure to this cuprate structure, and we actually made a new model for that, and could explain the data, again using dynamical mean field theory, because all these lattice models are very strongly correlated, very hard to solve. Okay, and it turns out, again I'll go quickly, I will not spend time on it. You can also do this single site dynamical mean field theory cannot capture D-wave superconductivity, because it involves more than one site. So in order to do that, you can take a cluster of sites and embed them in an effective medium. And this is called clusterdmft. It turns out quite non-trivial to invent something that retains something called causality. So I will skip that. I actually helped to invent the first causal method for doing this cluster DMFT, but the numerical challenges in solving this cluster self-constraint, like a many impurity Anderson problem, are substantial. So most of that has been done abroad because it involves extensive computer calculations. So let me skip this thing and show you some, for example, this is like calculation using this cluster DMFT, dynamical cluster approximation, which we invented. So you can see, you can get something like pseudo gap phase, D wave superconductivity, antiferromagnetism going down, something that looks like the cuprate phase diagram, but lots of the details are not quite there yet. So there's still a lot of work to be done here. Okay. All right. So this is like phase diagram of the 3D Hubbard model, which you can get from this dynamical cluster approximation. Okay, so there are lots of other challenges, development and challenges. You can generalize this to lots of other problems, and including non-equilibrium, etc., so on. So let me then end you. I started with impurity in a semiconductor. I'm back to an impurity in a semiconductor, but a new one. And this may run like the old N-type superconductors were running our lives. You may see a lot of this impurity in your future. Okay, so this is called NV center in diamond. So if you take diamond and replace one carbon with a nitrogen, it finds that energetically it's favorable to get rid of. If you try to heat it and then anneal it, it gets rid of another carbon from a neighboring site, and form this pair called nitrogen and then a vacancy, and it gets singly charged. So it's called NV minus center. Okay, and the ground state of that NV minus center is actually the lowest loving set of states is spin 1 electron. There are 2 electrons there, and so it's spin 1, and they're split in the way that I've shown. There's one state which is below, and then other 2 different values of the mz quantum number. Z component of the spin is like that. Okay, and then there are excited states, and there are optical transitions. And there's a very interesting thing you can do. So using light, there are lots of decay channels. You can arrange it in the separation between those ground state multiplets is very small, 2.87. So at room temperature normally, all of them will be equally likely. So the different spin configurations are all equally likely. But you can use light to send all these electrons in this state, the NV center in this state, to excited states, and the decay channels are such that more of them come down to that mz equal to 0 compared to the other ones. So if you keep cycling this, you'll find that after a while, you can put all the NV centers pretty much into that m equal to 0 state. So this is what is called spin polarizing these NV centers. So, and then if you put on a magnetic field, then you find that this thing will split in such a way that there are 2 of them which are close by, and then another one which is slightly elevated. And those 2 states you can use as a quantum bit called a Q bit. Okay. And then, so you can do the spin polarization. So this has all kinds of applications in quantum sensing, because you can achieve enormous spin polarization of these NV centers. People think that you can detect magnetic fields up to nano Tesla and electric fields of 10 volts per centimeter. That means you can make out if there's one electron, right? You can approach 1/10 of a centimeter away, and you'll know that there's one electron there. It's an amazing sensitivity to electric and magnetic fields. And also, because you can spin polarize them, you can do something very fancy. I'm just done in 1 minute. So you can like crush this NV center diamond where all the spins have been polarized, dissolve it in water, let's say, put it in water, it won't dissolve. But then the spin polarization that is in the NV minus centers in the diamond will be transferred to the nuclei of the water molecules. Okay. And then you filter out the diamond particles and get a patient to drink this water, and then ask them to do an MRI. Now, you know that MRI costs you, I mean, like it's huge machines, because you need a huge magnetic field to polarize all these nuclear spins, which are very tiny, and then that's why it costs so much, right? But you already via hyperfine interaction, you already transferred the spin polarization of the electrons to the nuclei. So it turns out that you can just, with very small magnetic fields, now you can do MRI imaging after the patient has drunk this water which has been already polarized. So you may find, I don't know if you're fans of Star Trek and so on, with science fiction, they have a machine called tricorder in Star Trek, which you go around on the body and then you can image everything. So maybe somewhere in the future, with these NV centers, you may have a handheld MRI machine. So that's another quantum impurity that's going to become very important for quantum computing and sensing, all kinds of applications. So, sorry, let me. So I've, many students and colleagues have worked with me, and many people have mentored me. So I should acknowledge all their contribution in my scientific evolution and growth. And thank you for your attention.